Thank you for inviting me to speak. I have been focused on the origin of the Earth and the Moon since Mattia was a postdoc at Harvard working with me, and I will tell you about some of our new ideas about making the Moon. And I begin with this art graphic of the early Earth, mostly to remind everyone to be thinking about water during everything I'm telling you, but I will be talking about the state of the Earth a bit before this comparatively peaceful image from the Hadean Earth. So the context of understanding the origin of the Earth and the Moon is the basic mechanics of planet formation, where dust collides and grows into larger planetesimals until protoplanets are made. And when the protoplanets form, they collide with one another to make larger planets. And this last stage of planet formation is known as the period of giant impacts. And giant impacts are generally thought of as being random energetic events. Anytime you see something quirky about a planet, we invoke giant impacts to explain it, whether it's the large core of Mercury, the retrograde spin of Venus, or our large moon. And today's talk will focus on the questions that remain. And the more we interrogate the origin of the Moon, the more questions we come up with. And at present, we'll consider the origin of the Moon an unsolved problem. And over the course of the hour, I'll explain the details of why it remains an unsolved problem and hopefully point us in a direction that we consider very promising. This is an accidental view of the Earth and the Moon. This set of data were planned without realizing that the Moon would happily transit in the middle of it. But it's quite fortuitous, and it reminds us of how large our Moon is compared to Earth. It is 1.2% the mass of the Earth, and orders of magnitude more massive than the comparative sizes of the Moon, say, around the giant planets. And so one of the puzzles is, how did we make such a large Moon? Our Moon is similar to the Earth in many ways, but has a few key differences, including its small iron core and its comparative dryness. The giant impact hypothesis for the Moon has been the working hypothesis for some 40 years now, but we really don't know how to think about giant impacts. It's not an everyday experience. And so we are guided by what we perceive as very energetic events. And it's true that a giant impact is very energetic and that deposition of energy is key to what happens next. But it's not an event that doesn't follow a set of rules that can be used to understand what happens, including what happens to the water. And I wanted to include some comments about water and the giant impact because there is a misconception that persists in the public and in space agencies that giant impacts will naturally remove all the water from the Earth. And Rosetta gathered some lovely data on the deuterium to hydrogen ratio of a Jupiter family comet and commented that the puzzle of where the water came from and the origin of the Earth is related to the idea that we would have lost all of our water. So do we think of these energetic events like a hot plate and a beaker and a vacuum pump? And if you have this system in the lab, it will naturally remove, and very quickly remove, volatiles from a silicate melt. And is that an appropriately analogous system? But really the reason why we care about the origin of the Moon and the Earth is this question. And we want to be special but not too special, but because we're scientists we frame it in a different way. We say, are we probable? Do we expect to find other Earths? But because we don't see an Earth-Moon-like object in other places, we want to be probable but not the common outcome. So we have constraints on the origin of the Earth and Moon. And the primary data that were used to drive the idea that the Moon formed from the Earth were gathered in the Apollo mission where the bulk composition, that is the relative elemental ratios, and the isotopes, the particular differences within a single element, are similar to what we call bulk silicate Earth. And you can think of bulk silicate Earth as everything except the core. So the rocky parts of the Earth are similar to the Moon, with the exception that the Moon is depleted in volatile and moderately volatile rock-forming elements. And so I'm not talking about water specifically here. The Moon is dry compared to the Earth. But we're talking about the elements that will outgas at the lowest temperatures from a silicate melt. And the interpretation that the geochemists came up with soon after seeing this data are nicely summarized in this quote from one of the early papers, that the Moon formed by condensation of the evaporated Earth's mantle, and that the energy for that was driven by an impact event, and that this happened after core formation on the Earth. And the similarity demanded that we have a genetic relationship between us and the Moon. And over time, this relationship has become more and more robust as our analytic facilities in the lab have made it easier for us to measure isotopes and compositions more precisely. Okay. So the giant impact hypothesis was developed in the 70s independently by two different groups who approached it in those slightly different ways, but basically came up with the idea that a single, although possibly multiple impact events could launch material from the mantle of the Earth into orbit, and the Moon would accrete from that material. And a set of constraints, observational constraints, are used to define the standard model, and that is the present-day angular momentum of the Earth-Moon system. And the masses of the two bodies, although the giant impact itself just makes a disk and not the Moon, and so what we're using as a constraint is the mass of the disk around the Earth, and that this disk is depleted in iron. And in most of the simulations, if the iron core of the impactor merges with the growing Earth. And this impactor has been given a name, Theia. It is the unknown object. It's large enough that we consider it another planetary embryo or another protoplanet, striking the Earth sometime between 30 and 100 million years after the start of the solar system. The canonical solution is about a Mars mass impactor, a little larger, impacting just at or above escape velocity at an oblique angle. And this has been developed through the use of computer codes that find solutions that mimic these constraints. And so I'll show you an example of these computer calculations of what I'm calling the canonical impact scenario with the Mars mass impactor at escape velocity. This is what you find in the textbooks when you look up the origin of the Moon. These calculations are conducted with a computer code called smooth particle hydrodynamics. And in this type of code, each mass element is represented by a particle which has a fixed mass but changes density as it's heated or cooled or compressed. And the relationship between the pressure and density of these particles is determined by something we call an equation of state, which just tells the code whether or not it's an iron particle or a rocky particle in this case. Self-gravity is included in these calculations, but the materials are considered strengthless in that they're like a fluid. And under the conditions of a giant impact, the material strength in this early time is of secondary importance, although it is important for some details, of secondary importance for the outcome that we are trying to match today. The colors here just represent materials, the gray for the iron, and the colors for the mantles. This is a slice through the middle of the object. So we're just looking at the lower half of the event. And what you're going to pay attention to is where the materials end up. So the impactor is sheared into pieces. The core is broken into this nice long string of impactors that will rain on down. The Earth itself is deformed, and this non-spherical Earth torques material into orbit. And it's this transfer of angular momentum between the debris and the non-spherical Earth that allows some of the material to gain sufficient angular momentum to remain in orbit rather than falling onto the Earth. And there's moonlets of different sizes, but in general, this is a partially vaporized hot disk from what's called an n-body code. In this case, each particle has a fixed mass, and the orbits of the particles are calculated around the Earth. The units here are Roche radii, approximately 3 Earth radii, and this is the size of the proto-Earth. And within a Roche radius, a satellite will be sheared apart by tidal forces, and beyond the Roche radius, a satellite can survive. So as you see in this first time step, the calculation began with a swarm of debris to mimic what was found in numerical simulations of the giant impact. And this debris collides with itself, and as it collides, the particles are assumed to merge and grow. There's no equation of state to these particles. They just merge and grow and remain solid particles, whereas in reality, there is heating and vaporization that occurs that's been neglected in this particular calculation. In this calculation, the particles accrete and grow into a moon very quickly. You could, under these ideal circumstances, grow the moon in a month. That is not how fast it could grow, because there's too much heating in that time scale to grow the moon in a month. And so more modern calculations include some parameterization of how to handle the fact that this is a partially vapor disk. And then the accretion of the moon is controlled by the cooling time. And now that's years to hundreds of years to cool the disk down and accrete a moon. So the time scale for moon formation is something 1 to hundreds of years. In all of the calculations, simple and more sophisticated, the accretion efficiency is rather low. Most of the material in the disk falls back down onto the Earth, and a small fraction forms the final moon. And so most of the time, the disk needs to be more than twice a lunar mass in order to make a moon, or have a chance to make a moon. And the reason for this is that as material is torqued outward into this growing moon, that carries most of the angular momentum outward. And to compensate, because angular momentum is conserved, mass needs to move inward. And more mass needs to move inward to compensate a certain amount of mass moving outward, because angular momentum is related to the distance from the central planet. And so angular momentum is moving out and most of the mass is moving in, and that defines the inefficiency of lunar formation. And so in most cases, when one starts with a calculation from a giant impact simulation and then uses that to calculate the size of the moon, most of the moons that form are less than a lunar mass. It is not a common result from the giant impact itself. And the physics of what happens in a vapor-rich disk is complicated and not fully understood, and we'll get back to that. So as I mentioned, the Earth and the Moon have very similar geochemistry, and the elements that are highlighted in this similarity are shown here. And the details of how the isotopic variations arise in the solar system are not so important as much as for you to appreciate that the isotopic variations that we see between the Earth and meteorites and other planets arise from many different processes. Some are nucleosynthetic in origin, some arise from variations in the solar nebula, and some arise from processes that happen on a planetary body themselves. And so when we compare the Earth to any meteorite or meteorites that we believe are from Mars, each object has a unique set of isotopes that we use as the thumbprint to categorize material from different parent bodies. And so because we observe that each body has a unique thumbprint, we would expect that two protoplanets that collided late in planet formation should have a different isotopic signature. And therefore, the impactor onto the Earth should have had a different isotopic signature. And in the canonical model, most of the disk is made out of the object that hit us. And therefore, we expect that it has a different isotopic signature. And thus is the conflict that we have between the observation and the standard giant impact hypothesis. And it is a major problem. So to be clear, any giant impact that satisfies the angular momentum constraint. If you take the lunar orbit and integrate backwards in time to the Roche radius, the Earth would have had a 5-hour day. So the giant impact sets up an Earth with a 5-hour day. Any impact event that gives us that and the mass of the Earth and about 2 lunar masses in the disk has most of the material in the disk coming from the thing that hit us. And so we have a fundamental conflict between the physical theory for making the moon and its geochemical prediction and our observations. And there have been 2 major ideas to solve this conflict. The first is the impactor had the same isotopes. The argument for this is a little subtle in that it asks us to consider what we cannot see in the meteoritic record. We have a record of primitive bodies from the solar system that must be incomplete, in that there's no meteorite that looks like an Earth meteorite. Right? They all have something different about their chemistry or their isotopes. There is a class of meteorites called enstatite chondrites that have very similar isotopes to the Earth. Not identical, but very similar, and much more so than any other primitive meteorite group. And these are a collection of nebular dust at the gram scale. And it has isotopes that look like us, a planet many orders of magnitude larger. And what some researchers, Nicolas Daffat in particular in a recent paper, have argued that this is too hard to be a coincidence. And the best explanation is that there was a region in the inner solar system where the isotopic components formed from all these different ways had homogenized through a disk process in the planet-forming disk around the sun. And that original material found its way into meteorites and found its way into the Earth and had subsequent chemistry happen to them because they're quite different chemically, but that their source materials were isotopically the same. And this could solve one of the problems. It does not explain one of the isotopes, which is the tungsten isotope system, which is the isotope that tracks core formation on the body. So it does not explain why the moon should have the same tungsten isotopes as the Earth. And it does not help us explain the problem with forming the large mass of the moon. So it is a partial solution, which may or may not be true and will remain neutral about this, but it's an incomplete solution. The other solution that was proposed was that did not demand that the inner solar system be isotopically homogeneous, but suggested that the state of the Earth after the event was such that the disk and the Earth could mix mass. And if that were so, then a chemical difference in the disk compared to the Earth could be diluted so that the two could be the same, and that's what we see today. And this was a brilliant idea because the physical state of the Earth and the disk had not been considered to this level of detail, and it did raise the question of how does the system really behave in the aftermath of the moon-forming impact. The model, as it was written down, has some problems under closer scrutiny. In particular, one of the main problems is if you exchange mass between the Earth and the disk, one would expect that one should exchange angular momentum. And if you do so, then the disk falls down, and you don't have a chance to make the moon. And so at this point, one might consider this option. And it's a serious one to consider because we now have a serious conflict between the predictions and the observations. And so one should at least step back and say, well, is there a better fitting model out there that we should turn to? And in the case of the moon forming, in the case of the origin of the moon, all the other proposed models were disproven by Apollo or earlier, in that capture and fission and co-accretion were mechanisms that all have their own fatal flaws before we ran into our isotopic crisis here. And so we have nowhere else to turn. And so A couple of years ago now, the only thing left to do in the context of the giant impact model is to evaluate our self-imposed constraints. And of the constraints that we were trying to match with the giant impact, the one that was most restrictive was the angular momentum of the system, having been unchanged. And that assumption was relaxed in that the angular momentum of the present-day system did not have to be set by the giant impact itself, but could be set by some dynamical process that occurred afterwards. In which case, we have a lot more leeway with the moon-forming event as long as there was something else to turn to that could bring us to the present-day angular momentum. And so that led to the proposal of two tweaks on the moon-forming impact event itself, with the goal of making the disk out of the same material as the Earth. And you could do that a couple of ways. In a model proposed by Robin Canup, two approximately half-Earth-sized protoplanets collide at an oblique angle, and the final planet is a merger between the two, and the disk is composed approximately equally from the two bodies. In a different geometric scenario proposed by Mattia and myself, the Earth was nearly fully grown and spinning quickly already, and a small fast impactor hit it and launched material primarily from the Earth itself into orbit. And again, the disk and the Earth are composed about of equal proportions of the two bodies. And so this is an alternative way, sort of a brute force way of solving the isotopic similarity by saying the source materials in this case were the same, and that occurred in the process of the impact event itself. After the formation of the disk in these scenarios, the Earth is spinning between 2 and 3 hours and has 2 to 3 times the present-day angular momentum. So after the moon forms, resonance needs to transfer angular momentum away from the Earth-Moon system, and that a mechanism was found and published in this paper where the evection resonance transfers angular momentum from the Earth-Moon system to the Earth-Sun system. And that is a key step, a key requirement of a high angular momentum impact scenario is that some dynamical mechanism can remove angular momentum. So let's take a look at this scenario. So I'll show you an animation, a couple animations of the fast-spinning Earth case. I'm starting with a side view of the planet to emphasize that when a planet is spinning at 2.5 hours, it is quite oblate. And in the limit, it's got a 2-to-1 equatorial to polar axis. So this is not the planet as we know today. And in this case, the impactor is a half Mars size, coming in quite quickly, 20 kilometers per second. We're going to rotate so that it's a top-down view, same color scheme as before, and we're just looking at the lower hemisphere. The impactor penetrates all the way down through the mantle to the core, opens up a huge hole in the planet, and flings material outward. And over the course of several hours, oscillates to try and regain gravitational equilibrium. And what you should notice is, in this case, that most of the particles that are in orbit are green, now derived from the proto-Earth. The cores have merged. There's very little iron in orbit. And the Earth is hot. This is a very energetic impactor. These particles are the ones that we called atmosphere, and these particles out here are the ones that we call disk. And it's about 2 lunar masses, and the proportion of material in the proto-Earth and in the disk are about the same. And in this case, because it's a smaller impactor, most of the material is derived from the proto-Earth. Now, when I show these movies, I'm always a little worried that people are misinterpreting them, because a Lagrangian calculation where each little ball represents a fixed mass on a black background might lead people to think boiling into space, and I don't want you to think that. And so I'm going to show you the same calculation, but I'm going to take the particle density data and interpolate it so that you're looking at a cut where the colors represent density. So the scale bars over here, where the reds are the iron core, and there's a less compressed core in the impactor, and we'll make vapor. This is again a slice through the equatorial plane, the impact plane, and here you see that this is vapor being formed, and the planet is deformed and oscillating, the core is deformed and oscillating, and this vapor-rich structure around the planet is what we label disk, in that it's got enough angular momentum in it to stay in orbit, but it's really a big continuous structure, or a super atmosphere is one way to think of it, and it is not boiling into space. Within the disk, it's particles that are boiling in a substantial atmosphere that's hundreds of bars out by the Roche radius. So the first question you might ask about this new idea of a fast spinning Earth or two half-Earths colliding is, do we expect planets to be spinning quickly? We don't see any terrestrial planets today with a day of 2 to 3 hours. Is this a reasonable expectation? So very few planet formation simulations have tracked planetary spin. And there's a very simple reason, in that we do not know how to model it correctly. And what has been done in most simulations to date is to take the two bodies that collide, assume they merge completely, and sum their impact and spin angular momenta. And when you do that, you find that all the planets are spinning near their spin stability limit. And that calculation is shown here in the black dots. So these are different n-body simulation of terrestrial planet accretion, similar to the lunar talk that you heard earlier this month. And these are different size final planets focused on the terrestrial planet region. So half Earth mass to 1.5 Earth mass. And the black dots and the error bars are the range of spin states they find at the end of growing the planet. So after a sequence of giant impacts have led to the final planet. And this line here is about the spin stability limit at 2-hour spin of what we expect for these size bodies. And they're all spinning at their limit. And so we know that, or faster. So we know this is not physical, and it's not physical because of the assumption of perfect merging. It takes just a very little bit of debris to carry away a lot of angular momentum. And in particular, one of the main artifacts in this calculation is that a large number of collisions are grazing. And they're so grazing that the two bodies hit and then keep going, whereas in the code they had been merging. And if they hit at such an oblique impact angle, there's a large impact angular momentum component, which is not a true outcome. And so the same authors subsequently modified their code to take into account these so-called hit-and-run events, and to not have the planets merge, but to keep going along on their orbits, and then they will most likely recollide again a little bit while later, but in a more head-on manner, and then the angular momentum component of the impact event is diminished. In this case, they found the red dots and error bars for the spin states of their final planets. And the mean value is more than 2 times the present angular momentum of the Earth-Moon system. And about half of the time, the final planets are spinning between 2 and 3 hours. So because giant impacts involve oblique impacts between large bodies, they naturally lead to high spin states. It's an expected outcome. And there is the occasional case where they impact in the opposite way and slow down. But in general, the cumulative effect is to lead to fast spinning planets. And then you ask, why aren't we all spinning quickly? And then you can talk to Mattia about the subsequent dynamics that affect the spins of planets. The spins that we see today are not the original spins. Okay, so one, we do expect planets to be spinning quickly at the end of planet formation. And what I want to focus on the rest of the time is, what does the Earth really look like after such an event? Because that will determine how the moon forms. And I'll explain how it's different from the canonical case. and propose our ideas of how the moon accretes under a high spin case, explain why we still have the water that we started with, and discuss the idea of probability. Okay. So to date, under the fast spinning case, only these two specific scenarios have been studied in detail, and the wide parameter space of giant impacts that could lead to the final planets has not been explored. And so we are looking at the problem through, I would say, limited information at this point, and I'll get back to that. So let's talk about the state of the planet. It is hot. I showed you a plot where much of the planet had been vaporized, and the vaporization occurs by deposition of energy from the impact. The projectile comes in, deposits its kinetic energy into the proto-Earth, and generates a shock wave to transfer that energy through the body. So the color code here is the magnitude of the shock pressure that's generated from this impact event. So the hotter colors are higher pressures, and I'm contrasting the different moon formation scenarios. These are the fast spinning Earth scenarios with different impact velocities, lots of reds and vaporization in the impact hemisphere. The canonical impact coming in at escape velocity with a Mars-sized impactor is comparatively a low energy event. And 2 half-Earths is something intermediate. In these cases, in the high momentum cases, a substantial fraction, several to 10% of the planet is vaporized. And the highly vaporized material forms the outer layers because it's hot and less dense and more buoyant. So in the readjustment of the planet during trying to re-achieve gravitational equilibrium, the hot stuff ends up on the outside. So this is what we call a provenance map, where the colors just tell you where the material ends up. So it's telling you what material ends up in the hot parts of the disk and the colder parts of the Earth. So first look at the final time step. This is 2 days later. Again, a slice through the equator. The gray is the core. The purple is the lower mantle. Blue is upper mantle. Atmosphere is yellow. And the disk is green. And the yellow and red escapes. Red is material that's ejected from the system. There is a substantial amount of debris, several lunar masses of debris from these high momentum events. And the debris is sourced back at time 0 from near the impact point, as you would expect, because this is the material that's deposited the most energy and can reach escape velocity from the system. The atmosphere and the disk are from similar regions because those are the material that just didn't quite reach escape velocity. And then the colder opposite hemisphere ends up forming the lower mantle. And so this highly shocked material forms the outer layers of the system after the impact event. And what kind of impact energies are we talking about in the context of planet formation? So we can look at the n-body simulations of growing Earth-like planets and calculate the specific energy, the energy per unit mass, for each giant impact event. And so I just mined some published n-body simulations by Sean Raymond of growing terrestrial type planets under a range of conditions and calculated the specific energy. And this is just a measure that we've developed of energy that takes into account the mass ratio between the two bodies and the impact angle so that it can be an apples and apples comparison. And here's the histogram of what the energy per unit mass of the larger body, and the green line is the energy per unit mass of the smaller body. And the bars indicate the moon-forming scenarios. The canonical Mars-size impactor is a roughly order of magnitude less energetic event compared to the new high angular momentum cases. But the high angular momentum cases are the mode of what we find during the giant impact stage of planet formation. So about 20 to 25% of impact events occur in this high energy range. So this goes to the question of the stochasticity of giant impacts and why some of them are less energetic than others. There's a range of impact parameters that occur, and the types that we're talking about for this potential moon forming scenario are a substantial fraction, but there are plenty of other outcomes that can help explain differences between us and the other planets. So now I'm going to talk you through the vaporization of the Earth, and I'll introduce the idea of an entropy diagram and contrast it with a standard pressure temperature plot. So if one is familiar with phase diagram plots, say of water, there's a solid region at low temperature. At high temperatures, water is vapor, and at high temperatures and pressures, it's a supercritical fluid. When a parcel of material is shocked, it achieves a high pressure temperature state that lies somewhere on the red line that we call the shock eugonio. And material that is shocked to a high pressure state and then decompressed back down to ambient conditions, it's a transient event, can be vaporized if it's shocked sufficiently high that when it decompresses, it intersects the liquid vapor phase boundary. And this is easier to see in a pressure entropy plot, where one can think of the latent heat of vaporization as the temperature times the change in entropy on this boundary. So on this phase diagram, liquid occupies this space, vapor this space, and solids are lower entropy states. Starting with the solid Earth and shocking to high pressure, decompression happens quickly, doesn't have time to exchange heat with its surroundings, it's quasi-isentropic, and one can calculate how much vapor is generated by using the lever rule, knowing the entropy in the shock state. When we look at the calculations of making a moon under a giant impact event, much of the mantle is shocked to hundreds of gigapascals. And under these states, when decompression occurs down to this ambient atmosphere that we have around the planet of hundreds of bars, much of the material can be vaporized. And we have done lab experiments to be able to calculate how much vaporizes. And this requires high energy platforms like the big laser at Lawrence Livermore Lab. But we have now done experiments on different mantle phases so that we can tell you the shock conditions needed to vaporize these materials. And so this entropy pressure plot helps us describe the state of material after the impact event and how much is vapor. And so this has been done and published recently by Miki Nakajima and Dave Stevenson, where the entropy state of the disk has been calculated in the code, and here is the same plot, but now with temperature, entropy, liquid on this side, vapor on that side. If there's an intermediate entropy, it means you're partially liquid and partially vapor, sitting on the phase boundary. And if you're closer to the vapor side, more material is vaporized. The high angular momentum impact events generate mostly vapor around the planet, and the canonical impact events generates mostly droplets. And it's this difference in state that ends up being very important for what comes next. The disk itself is defined by looking at the orbits of the particles around the Earth. This is a side view from the canonical paper defining the standard giant impact scenario. And these are, again, SPH particles, now with the color code of temperature to show you how hot the Earth is. This is showing the outer layers of the Earth, and it would be glowing as bright as the sun if you could look at it, if you could have seen what happened next. And the particles in orbit are determined by instantaneously cooling them onto equatorial orbits, and just whatever doesn't intersect the planet we call disk, and whatever has an orbit that has a semi-major axis larger than the radius of the planet we call disk, and whatever intersects the planet we call planet. And so this definition implies some known radius of the body, but when there's a fast-spinning planet, it's quite oblate. And so we need to estimate the radius of the planet. And we've done that by calculating fast-spinning numerical planets, where using the same SPH code, using an iron and a rock layer of Earth mass planets with the right proportions for the core and the mantle, can calculate the equatorial radius while we increase the spin period of the planet. And we find that the limit for a two-layer planet ends up being about 2.3 hours. And you can't spin it any faster without particles flying off or losing mass. So that's the spin stability limit of the body, and in that state, it's so oblate that its equator is about twice as large as its pole. So now we know the radius of the planet in this case, but these planets are cold planets without a hot atmosphere around them. Jupiter is our main example of an oblate planet, and its difference is only about 7%. So we're talking about quite extreme states for the early Earth. So let's look at our conceptual idea of these states, these vapor-rich states. So here's a cartoon prepared by Simon Locke to contrast the states after a canonical impact and these high momentum events. So now we're looking at a side slice view instead of a top slice view, showing the core and the hot Earth, which is mostly melted with a hot vapor atmosphere around it, and this disk that's in orbit that's a mixture of droplets, represented here in red, and vapor cooling out here in blue. And some of the disk extends beyond the Roche radius. And the trick, and much of the mass can be within the Roche radius, and the trick in this case has always been how to transfer material from inside the Roche radius outward to be able to grow the moon before the system cools and falls onto the Earth. Okay. So at the same scale, this is what the planet looks like after a high momentum case. It is a big football, and it is a continuous structure from the deformed core through this hot supercritical fluid mantle into an atmosphere and disk. And here the distinction between what you call planet and what you call disk is entirely artificial. We have defined a disk and written down a mass and a composition based on this idea of instantaneously cooling the system down, what would stay in orbit and what wouldn't. But that's not the stage that we're at when we're trying to make the moon. And so the particles in the SPH code that comprise the disk are a set of particles in the outer layers, but they interact with particles that we would call atmosphere. Okay. And it's a continuous material. So there's no distinction between mantle, atmosphere, and disk other than there's a big density gradient through it. And so it's such a strange structure, we have a nickname for it. We call it the mad planet, after this continuous mantle, atmosphere, disk structure. And the main point is that these are fundamentally different beasts, apples and oranges, and what happens next is very different between the two. And it's because what happens next to form the moon is fundamentally governed by dynamical and thermodynamic discontinuity between a planet and a disk versus this continuous structure around a fast-spinning planet. So let's look at this in this phase space diagram again. So this is a sketch of what I've been trying to explain of phase boundary with liquid on one side and vapor on another, and the more highly shocked materials have higher energy. The planet itself is entirely fluid in that it's a hot, under high pressure material, and as one goes to larger radii, intersects with the atmosphere and intersects with the disk. But it does it in a smooth and continuous fashion. So there's no phase change, no rain in this atmosphere at all. It's one continuous fluid. The canonical disk is colder. It formed from material that was nowhere near as highly shocked up here, and it's mostly droplets. But the planet itself has a pure vapor atmosphere. And so droplets that fall inward encounter the gas of the atmosphere of the planet that's rotating more slowly and can fall in. But in this case, droplets moving inward would vaporize and then continue in the circulation of the atmosphere. So let's look at the velocity structure in these two bodies. This is a plot of radius starting at the center, moving outward. The Roche radius is about 18,000 kilometers. The line here is Keplerian velocity. So a perfectly circular orbit around the Earth. This is the angular velocity that that particle would have. Out here at the Roche radius, angular velocity. And now let's look at the velocity profile through the canonical case. This is the canonical case. These red particles are the disk. They are basically in Keplerian orbits, these particles. And then there's a bit of interaction with the atmosphere and into the mantle. And I'm not showing the core in this plot. So this is a 5-hour rotation, and the inner part of the disk is rotating more quickly. So particles that are falling onto the planet encounter a more slowly rotating atmosphere and are dragged inward. And so this is a one-way loss. If anything accreting to the planet accretes to the planet quite easily and stays there. In the case of the high angular momentum state, this mad planet, the planet is rotating more quickly than the outer layers. There's differential rotation in this body. And material that's in the outer layers that tries to move inward is actually encountering a shear flow that's moving faster. And the direction of the shear flow is like a Keplerian disk. It transfers angular momentum outwards. And so in this case, you can't fall onto the planet. There's thermal pressure supporting the whole structure, and you have a headwind. You can't fall onto the planet. And so the dynamics of what happens next is different. In this case, because of this dynamical and thermodynamic barrier, it's quite difficult to mix across the two. And that has been the problem with the idea of mixing between the disk and the planet in the canonical case, that boundary is a fundamentally difficult boundary to get across. In the high angular momentum case, there is no boundary. It's like mixing within Jupiter. It is big, eddy, turbulent convective cells, rotating on a time period of 2.5 hours. It is mixing on the time scale of a week. And so even though we've placed hot projectile material in certain places on this object, they will be mixed in with the planet and has a much more capacity for isotopically equilibrating whatever the two bodies were that made this structure. So in the canonical case, lunar accretion is inefficient because of all of the barriers I've talked to you about. And in this high angular momentum case, there's just a fundamentally different accretion process. Droplets sourced from the whole Earth, the bulk Earth, are condensing in the outer layers beyond the Roche radius. This is a structure that overfills the Roche radius. And those droplets, if they can grow into large enough sizes, decouple from the gas and can form the moonlets that grow into the moon. And in this way, we can achieve exactly what the geochemists described 40 years ago. The moon is a partial condensate of the Earth formed from the highly shocked vapor atmosphere after an impact event. And that this partial condensate of the bulk Earth explains what we see in the moon today. In many cases, under a sufficiently energetic impact event and high spin, more than a lunar mass exists outside the Roche radius. So nobody knows how to calculate this numerically yet. So the goal next will be to see if we could get our size moon out of this structure. What do you need in order to condense out something as large as a lunar mass from this structure? It should be more efficient than this case. Okay, let's talk about this. We've made this big boiling vapor ball of the Earth. Would we have lost all of our water? For a late moon-forming impact, we actually expect there to be oceans. That first image that I showed could have been the Earth before the moon-forming impact. At the end of accretion, there's no big temperature input onto the surface anymore, and so water that's accreted to the Earth can condense and form an ocean. A giant impact event can blow off the atmosphere by this shock wave running through the planet. So here are snapshots of an impact event with density as a contour. Here's the impact. This front that you see moving through is the shock front. When it reaches the opposite side of the planet, it moves the surface to such high velocity that it kicks the atmosphere and sends a shock wave up through the atmosphere on the opposite side and accelerates the mass to escape velocities. It takes a very energetic impact to remove all of the atmosphere. These high angular momentum cases are very energetic impacts, but they don't remove all of the atmosphere, but they can remove a substantial fraction. We're talking about the gas. If the water is present as a condensed ocean, it does not remove the ocean. It's quite difficult to remove the ocean and the crust entirely in this type event. And so we expect that the water will be vaporized, but that the vapor will be bound by gravity. And even though, and in this mixture, there are volatiles, the outer layers may slowly escape. You may leak out the light elements at the top, but it's a slow process, and the whole system will cool in about 1,000 years. And so you cannot lose all of your volatiles in this process. So if the moon is a partial condensate of this massive structure, and that massive structure has volatiles, the moon will receive a portion of it, a little bit that condenses from the outer edges, but not be entirely dry. So finally, I just want to say that the question of probability now rests on the idea of what does it take to make this structure to be able to make a moon via this mechanism. And you need two components. You need the sequence of events that leads to making the moon end up with a fast spinning planet. It could be spinning before the impact event itself that triggered moon formation. It could be spun up or spun faster by that event. And it needs to be an energetic enough event to vaporize several weight % of the planet or more. So those are the two criteria. They do not have to be achieved at from the same event, but they need to be achieved through the combination of events for the moon forming impact. And if that is the case, then many different specific scenarios of two different sized bodies at a certain velocity and impact angle could generate this structure. What's been studied to date were special cases where there was no post-impact mixing. These cases were tuned to not require post-impact mixing, and the irony is that it generates a structure that naturally mixes. And so we can have many different impact scenarios make a mad planet, and the true probability will need further n-body simulations that actually keep track of spin and fragmentation. So making the moon is a multi-step process, and that middle step is really hard and key to the process. The first step is the first day with a giant impact that generates this high energy, high spin condition. The next step is condensing out the moon from this well-mixed structure, and the final step will be after the moon forms, reducing the angular momentum of the Earth-Moon system as a key part of the high angular momentum framework for making the moon. This is a nice view. The moon has seen a lot. The moon got to see the Earth in this crazy state that we don't get to observe today. It may have looked more like a hot giant planet. And Kevin has shown this as the analog of the post-impact Earth. These are 5-micron images of Jupiter, but the Earth would have been glowing. It would have been fast spinning. It could have had bands the same way through the velocity structure. And I just want to end with thanking my co-authors, Simon Locke, my graduate student, Zoe Leinhart, and her student, Mia Mace, who we have collaborated on dynamical aspects of impact events, and Matya Chuk, to just say this has been a very exciting topic to investigate. Hopefully I've implanted the idea that the Earth did not always look like the Earth. The Earth could have looked like a very different beast soon after the moon formed. Thank you.
Thanks. Start with questions.
Yeah, thanks for the talk. Very interesting. I was kind of wondering a bit about the step that the moon actually condensates. You say there's mass beyond the Roche limit, but if I understand the Roche limit right, that is something you have in a two-body system, but you don't have a second body yet. Why is your mad planet not just cooling down and condensating back to one body?
It is, but it takes time to do so. And so it could take 1,000 years or more to cool, but the edges are cooling immediately, and they are beyond the Roche radius. And if the coalescing, so in order to cool the whole system down, to make a body that would be about 8,000 kilometers in radius, if you cooled everything down so that the silicate atmosphere collapsed. That process takes time. In the meanwhile, the outer layers that are beyond the Roche radius are cooling immediately, and they will form droplets immediately. And those droplets are in orbit. They have subkeplerian velocities. There's a velocity shear, a big drop in density. So it is a structure that, I agree, is not a two-body structure, but the outer edges of it are quasi-Keplerian, and those particles will collide with one another and can grow into larger condensates in this outer region. If angular momentum is being transferred outward, then those moonlets can move outward. It is not a system that anyone has studied quantitatively. It's not like the dynamics of a giant impact interior. It's not like the dynamics of a purely dynamical two-body system either. It's something in between. And so the way that we've envisioned this is that these outer particles can separate from the planet.
They separate from the gas motion, basically.
They have to decouple from the gas, yeah.
Hi. I have a question about the original impact in this model, which is, looking at your chart, there was a significant amount of mass that reached escape velocity.
Mm-hmm.
And I would assume that some of that mass mixture of both bodies would have, by chance, gone forward in the direction of Earth's orbit, and some of it would have gone backward in the direction of Earth's orbit, and eventually condensed into, small dust or meteorites or whatever, and then sooner or later we catch up to it, or it catches up to us, and it hits us again.
Yes.
Which would then tend to predict that there should be meteorites that have the exact same isotopes as we do.
Yes,
So, but we haven't seen that.
correct.
Why not?
So, it was a long time ago. They're hard to find. So much of the debris would have been reaccreted onto the Earth and Venus. And in an early part of Earth's history, much of the debris dynamical sweep-up time is in the first million years after the event. So that rock record is gone. Even the moon might have the tail, and there's some discussion of the tail of the debris even forming craters that we could see, since the moon would cool comparatively quickly.
That would be on the far side of the moon, right?
Well, it becomes an isotropic background debris, and so you would end up seeing it somewhere on the moon. It's not just on one side. But because that debris would have been swept up very early by all of the inner solar system bodies, we don't have that record. That's right. A tiny fraction would have made it out to the asteroid belt, but it would have been a tiny fraction of the whole system to find these meteorites. They would have been very small, as you say, so they would not have remained independent bodies. Yeah.
Following up on the first question, isn't the material on the outside of that just to have way too much specific angular momentum to fall back into a Earth-sized planet?
These systems are not supercritical in total, in that the disks that were made in all these cases need to have angular momentum given to the particles in the outer portion of the system, in that you could cool the whole system down and condense it down to the planet and not overspin the planet in most of the high momentum cases that are published. So you could imagine that in some cases you're very near the critical spin limit, and that you can't just condense it down because it would want to lose that mass. But in most of the cases that we're talking about, it's subcritical. So in principle, it can cool. It's just what happens before it cools.
But that's a total angular momentum constraint, and you'd have to transfer
still have to
substantial
transfer.
angular momentum inwards, which is energetically very difficult.
It's quite difficult to fall in, yes. It is quite difficult to fall in. And so it must involve the dynamics of the whole atmosphere to do so in order to be able to bring material in.
How visible would this thing be if it happens, say, in some exoplanet? Yeah.
So it would be very visible, and there have been some published studies by others on what would be the signatures of extrasolar giant impacts and hot post-impact magma ocean vapor atmosphere planets. And so these are detectable, eminently detectable, just short-lived. And so with enough planets, one would expect to see the occurrence, but they are still, you have to look at young systems, which has not been the main targets of exoplanets today.
For maybe less than a day?
Well, no, what you would mostly see is the high visibility of the debris in orbit around that star. And the hot planet itself is hot enough to be observed in that these are thousands of degree atmospheres transiently cooling down to the steam atmosphere. So you'd be looking for steam atmospheres. And their radiative properties are then determined by their atmosphere and whether they have clouds. And so the models of detecting a spectroscopic signature of post-impact magma ocean hot planet depend on its atmospheric properties. Yeah.
Okay, so that's it for questions. If you have further questions, please come up and you can ask Sarah directly. Let's thank Sarah again for her talk. And here's SETI mug with robots discussing how it impacts the Drake equation.
Okay.
Thank you.
That was very good.